So we're talking about parametrics. We've been talking about to some extent. So we'll take a little different take on them here. So here, we're going to get this one drawn using a table. Make a table. And sometimes you want to kind of pick and choose your t values. But here, I'm just going to do all the numbers from -3 to +3. If you're doing like square root or something, then you might be more selective. Before we actually do that, because we are going to use the table to produce a graph, I want to go ahead and convert this equation into rectangular form, okay? So to do that, I need to rewrite one of these as t equals. I'm going to do this one because, well, it'll be easier. So move the 6 over, it becomes a +6. And then take half of, except for I'm not going to distribute it. I'm going to write it as half of that, like so. Okay? And then I'll put this down here. I'm going to substitute that into the y equals equation. It says it's t squared minus 3, but t is this. So put the 1/2 parentheses x plus 6 there. Now here's the thing. When you go to square this, you can square each part. Watch this. You know, the rule is if you had like 2 times 3, actually let's make it easier. 2 times 5, parentheses squared. What's the answer? 10 squared is 100, right? You could rewrite that as 2 squared times 5 squared, and that's 4 times 25, which is 100. So I'm saying you can distribute if it's multiplication. If it's addition, you couldn't. So, which means this becomes 1/4, and that's just x plus 6 squared minus 3. And there you go. There's vertex form, the way you'd write in algebra 2. But I want to write it in like the way, you know, conic section standard form. So to do that, move the 3 over. And then the coefficient should be in front of the term. So remember, we're not going to distribute. We're just going to multiply both sides by 4. So you end up with a 4 in front of the unsquared part. So there's standard graphing form for a parabola, the way you write it for conic sections. Okay? And I'm not going to use these to graph it, though we could. But let's get at least the basic information. Which way does it open? It's a y equals equation with a positive coefficient, so it opens up, yes. And p is 1. If 4p is 4, then p is 1. And then also the vertex is where? Good, you got yourself. And you should be able to look at either form. The conic section form, you know, -6, -3. The vertex form, it's -6, and then you -3. Use the -3 as is, okay? Now, but we're going to go back here, and like I said, we're going to use parametric equations to come with this now. Go back to this. If you plug in these t values into this, start with -3, you get -6 minus 6 is -12. Plug in -2 here, you get -4 minus 6 is -10. And actually, this is just a linear function going by 2's, so it's going to go -8, -6, -4. If the slope is 2, that's what's going to happen. I couldn't recall the slope, but same idea. And if you want to check it, plug in this last t value, and if you plug in 3, you get 6 minus 6 is 0, so that's correct. Now, with the quadratic, I'm going to start in the middle, actually. If you plug in 0, you get 0 minus 3 is -3 for that y value. If you plug in 1, you get 1 minus 3 is -2. And if you plug in -1, you get the same thing, don't you? If you plug in 2, you get what? 1, and a -2, you get the same thing. And when you plug in 3, you get, you get 9 minus 3 is 6. And once again, -3 is the same thing. So there. Now let's plot these points. Look, the -12 is a little bit off the screen. I'm going to start over here. The y-intercept is at 6, so 0, 6, plot that. I'm going to work my way backwards. -2, 1, plot that point. -4, -2. -6, -3 is the vertex. Then it's what, -8, -2, -10, 1. And then you can see this one you should have in line with that one. And just estimate 2 points off. Now be careful when you draw this parabola. What I mean is you should not extend that past those endpoints because you're only doing t values from -3 to 3. And it's really easy to just draw your arrows out of habit. I know because I kept doing it. And then since it's parametric, you just need starting point and direction. Well, at t equals 0 is actually at the vertex. And then as t increased, the x value is increased, which means as t increases, you're going from left to right. And there you go, we're done. One thing I just want to stress again is that if you took the approach where you found the equation first, that's fine. You should be able to draw this parabola. The vertex was where we said it would. If p is 1, you'd go up 1, put the focus, go out 2p either side, you get those points. Yeah. But you definitely would need to calculate the endpoints. And so, if you, like I said, if you use the equation, I expect you to get these 3 points, but also calculate those points, and then because you have to know where to stop it, right? So just be careful. All right, do the next one. When you solve one of these equations for t, which one do you want to solve for t? The y equals or the x equals? Yeah, I would choose y. So you get t equals 1/2 y. And then plug that into your other equation. And once again it says t squared plus 2, so it's 1/2 y squared plus 2. Which when you distribute the exponent, you get 1/4 y squared plus 2. Which way does that parabola open? I don't know. Positive coefficient, but it's horizontal. This is x equals. Okay. Now I want to go ahead and write this in standard form once again. For that's vertex form, although you may not have had x equals equations. That'll be x equals for a horizontal parabola. Let's do the same thing though. Let's get it in standard graphing form for a parabola. Move the 2 over, and then you need to put the coefficient over there. So multiply both sides by 4, and there's standard graphing form. Which once again, we're trying to match this. Standard graphing form for a horizontal parabola. Okay? And then, once let's go ahead and get all the information. It opens right. P is 1 again. The vertex is where? Yeah. So, put the vertex at 2 on the x-axis. Go 1 to the right of that for the focus. And then go 2p either direction. And then this one, by the way, there's no restriction on t, so we just draw the whole thing. Okay, I can do this. I wanted them symmetric. Now, as far as finding the starting point, it's frankly easiest to look at the y equals equation. For one thing, it's simpler, and besides, you want to think vertically on this thing. In other words, if you plug in 0, you get y equals 0. So this one actually starts at the vertex. It doesn't always. This one does. And then it's obvious, as t increases, y will also increase. And so you can just know that. Or just try plugging in numbers. If t is -1, you get -2. When t is 0, you get 0. When t is 1, you get 2. So it's true. As t increases, the y values increase. There you go. Questions so far? We're not doing this one, by the way. Just to save time, I'm going to skip this one. And these, we're not doing it at all. We kind of chopped it down. Now this, you don't have in your paper. Just watch. We know this already. That's the equation. Parametrics for what shape? An ellipse, right? In fact, a vertical ellipse. Just watch for a second. To figure this out, I'm going to write cosine squared plus sine squared equals, this is an identity you should know. It equals what always? Okay? Now watch this. I'm going to multiply this equation by 9 and divide by 9. Not equation, this part, this expression, this term, I guess. Here I'm going to multiply by what top and bottom, do you think? Correct. 25. And we get there. Okay, that's sad. And then I'm going to rewrite this as 3 cosine parentheses squared, because I can. Sine. This then I can write as 5 sine of theta parentheses squared over 25. Now what? It says here 3 cosine is the same as x, so this is the same as x squared. And that's the same as y. Dun, dun, dun. Standard form equation for a parabola, vertical parabola, in fact. So we memorized it and said, okay, and always before the test, we just memorized, okay, if it looks like this, A is 5 and it's vertical, and then B is 3, the center is at the origin, and you write your parametrics from that. You can actually convert, do an actual conversion between the two. I'm not going to show it this way, but you can go backwards too. Now, one of these, just watch once again. Which identity do I use this time? Remember, there's 3 of them. There's cosine squared plus sine squared equals 1. There's I10 in a second. There's I cut cheesecake. Yeah. So 1 plus I10 in a second means 1 plus what? Tangent squared equals secant squared. Now, but I don't want it in that form because this is for a hyperbola, and hyperbola is written as a subtraction problem, right? So I'm going to do secant squared. If I move this over, it becomes minus tangent squared, right? So I'm going to rearrange this as secant squared of theta minus tangent squared of theta equals 1. That's the same identity. Now I'm going to take the same approach. Here I'm going to multiply by 81 top and bottom. And here I'll multiply by 25 top and bottom. And just bear with me. This is 9 secant parentheses squared over 81. What does that become? Nine secant is the same as what? Up here it says it's y, so that's y squared over 81. And this is then x squared over 25. And you have the standard graphing form for what kind of hyperbola, horizontal or vertical? Vertical because it has y in the positive fraction. And here, it's vertical because it has secant in the y equals fraction. So there you go. That's how you could actually convert. But we're not going to actually do those for this substance, so we're just going to move on. This you have in your paper. What I want you to realize is this example and the next one are the same parabola. We're just going to graph the rectangular equation right now. So put the vertex at 2. It's just standard, the parent function, shifted up 2. So from that vertex, if you're out 1 from the vertex, you go up 1. If you're out 2 from the vertex, put points 4 above. And if you're out 3, then go 9 above. Which, by the way, if you're at 2 already, that takes you to 11. So you'll be right off the screen there. And there's no restrictions, so just go ahead and draw the whole parabola with arrows. All right, now, it says it wants the parametric equations. Let's just do that real quick. Take this, rewrite it as x equals t plus 1. That's easy. Remember, if you want parametric, you need x and y expressed as a function of t. And this, all we're going to do is write x squared plus 2, except we're going to replace x with t plus 1. And that's all we're going to do with that. We're not going to try to simplify it or anything. It'll do. If you punch this in the calculator, which we'll do shortly, it will produce this parabola, okay? That's good enough. Now, the speed and orientation, here, I want to make a little table. And I'm kind of going backwards here, because I actually already have the graph, and I'm going to write these points in my table. So it was -3, 11, right? And that point was 9 above the vertex. This point's 4 above the vertex, so it's at 6. This point's 1 above the vertex, so it's at 3. And then the vertex is at 0, 2, and then you go to the other side, you once again 1 above the vertex, 4 above the vertex, and 9 above the vertex. Fine. But like I said, we're going backwards, and we're actually going to use this equation to figure out the time at which is each of those points. And it's easy. Just subtract 1 from the x value to know the time. So subtract 1 from that, subtract 1 from that, subtract 1 from each of them. Now I want you to label the whole thing. So it was here at time equals -4. It was here at time equals -3, and -2. It wasn't at the vertex at time equals 0, it turns out. It was here at time equals 0. And then it got to here at time equals 2. And when it says, graph the equation indicating speed and orientation, that's actually how you do that. So which way is it going as time increases? Well, from left to right. As far as speed, tell me, how long, let's say it's seconds. How long did it take to get to this leftmost point to the rightmost point? 6 seconds. Okay? So that's how you know the speed. Now, this next one, we're going to draw the same exact parabola, but you'll see the speed is different. So here, draw the parabola again. Same points. This time we're not going to bother with the table, so this will go faster. In fact, this time, I'm going to figure out the times now, and then we'll go figure out the parametric equations, okay? Now, so the time is just the x value doubled. Well, I'll start here. If the x value is 0, you double that and you get 0. So this one's actually at the vertex at time 0. If the x value is 1, if that's at time 2, when x is 2, you double that. When x is 3, you double that, because that's what this says. And over here, you double -1, you double -2, you double -3. So how long did it take to get from the left to the right this time? So was it faster or slower? Okay, let's write the parametrics now. This, you write, it'll be x equals 1/2 t, right, when you solve this one for x. And then once again, take your y equals equation, 1/2 x squared plus 2, and just put that in place of x. And that will suffice. You can simplify it if you want, but I'm not going to bother. And what I want to do is type these in the calculator. We're going to make them race. Now to do that, first of all, on your calculator, make sure you're in parametric mode. Go mode. You don't want function mode, you don't want polar mode, you want parametrics. And while you're here, go ahead and make sure you're in degree mode. We'll need that later for another example. And put it in simultaneous mode. You want them to race, so you don't want it to graph one and then another. You want them graphed simultaneously. Normally it's in sequential mode. Make it simultaneous, okay? Then you can go to y equals and go and type in your equations. What I'm going to do, by the way, is, so in x1, y1 type the first example, and then this is this second example we just used, except I changed the y-intercept because we're going to make them race and I want to be able to tell them apart. So just type it like I have up here. You don't. In other words, look, the X button, that's what this button right here, that normally gives you an X. If you're in parametric mode, it gives you a T. You should be in parametric mode. So go back to mode, okay. I'm saying, go to mode, make sure you're in parametric mode. Then when you go to y equals, you should see this. So if you're not seeing that, you're in the wrong mode. And like I said, to get the T there, you just press the variables button. If you're in polar mode, it will produce theta. Parametric produces T. Get these typed in. And hit zoom 6. And you won't really like what you get. I'll explain why in a second. Everyone got the equation typed in? Watch the equations. It's still going. All right, go back to y equals. And I want you, if it's not already set this way, go over here, put your cursor on the left, and press enter. And basically, you want the setting I have here, where it faces it. And if you just keep pressing enter, it cycles through the options. So make them both look like that, okay? And then you can see it as it draws it. That's for both those. Then go to Window, And when we did Zoom 6, Zoom Standard, it's set to the t values to things we don't want. Look, this one, it took 12 seconds, right? From t equals -6 to t equals 6. This one, it was actually smaller. In other words, I'm going to use these, -6 to 6. Now, you don't want to use 7.5 as your step if you're going only through 12 values. Look at that. It's horrible. If I make this 1, that's not bad. And by the way, you can see the top one was faster, right? Just to show you, by the way, like I said, if you're trying to go through 12 values and you make this go by, let's say, 4s, it's going to be bad. If I make this go by tenths, that's like 120 different points is going to calculate it. So it's going to be slower, but it's going to do a better job. And so that's what I want you to see is you want to have it, at a good speed so you can tell, which one's winning. I think that was a little bit too slow. But you can see that the top one's winning the race, right? The first example, which matches what we said. By the way, that one went off the screen because it was here at like 2 seconds, right? And so it's still going because we went to 6 seconds. So it's actually, the top one is drawing more of the parabola. This one only draws from 11 to negative, like 11 to 11. All right, there you go. You can play around with that if you want to. We're moving on. But you can see, you can adjust the speed of these parametrics if you want to. All right, look at this next example. It just wants, parametric equation. I'm going to show you a couple ways to come up with this, okay? And so, really you can choose which ones you like. Some are better than others, depending on what you're doing. So here, first of all, we need the slope. The y values do what? Decrease by how much? They decrease by 7, yes? And the x values increase by 7? So the slope's -1. Actually, the first way I'm going to write the parametrics won't even use the slope. What I'm going to say is, and I'm going to choose to use this point, is the x value starts at 23, and the x value is increased by 7, then that's your equation. The y values start at -15 and decrease by 7. And there you go. There's a pair. This is a t, and that's t. There's a set of parametric equations that would draw that line. Now watch this. If I were to keep that same starting point, or frankly, I could change out that starting point for this starting point. Any point in the line could go there. And if I change this to, let's say it's 14 and -14, well, that would produce the same line, but faster. Or if you really want to be creative, you can make it like -14 and +14, which is still a slope of -1, but now it goes the opposite direction on the line. So I'm saying with this kind of equation, you can kind of play around with the speed easily. That's your horizontal speed, it's your vertical speed, essentially. The other approach you can take, though, is just write your rectangular equation. So we're going to do point slope form, like we've done before. And this is the algebra 2 way we write it. There's no HK because we're not doing conics right now. And you just pick some point. I'll choose the first point. So you do y plus 15. Your slope is -1. And do x minus 23. Question? That's an M. It's just sad little M. It's a little better. All right, listen. And that's the slope. M always represents the slope. Okay. So here's your equation in rectangular form. And remember what I said. When you're writing parametrics, they need to be expressed so x and y are both functions of t. So first I'm going to rewrite this as y equals, which is simplistic. We just move the 15 over. So there's my rectangular equation written as y equals. And if you can do that, all you need to do is replace x with t. So one equation will say x equals t. The other equation, you simply replace x with t. And those parametric equations will produce the same line. So there's 3 different answers for this question. And what I'm saying is, in some application problems, you might choose this way, but then again, you can always do this way. whichever suits your fancy. Well, like I said, frankly, this one, I don't know what either one's easier. This one's kind of the older way to do it. I mean, you should write the equation for the line since algebra 1, right? And so this, just write the equation for the line, and as soon as you have y equals, replace x with t, you have parametric. It's quick and easy. This is a new way to do it. It's not hard, though. And so, and certain application problems match this, you can write this directly from the problem. It's obvious. And so it has an advantage in that respect. We'll see you tomorrow. All right, look at this. Last thing, we're talking about projectile motion. You have these equations to calculate the horizontal and vertical distance traveled based on time. So read this problem. And while you're reading, I want you to figure out which of those numbers is extraneous information. But don't blurt it out, just read. Yeah. And it's good to know, but we don't need it for this problem. We do know the height at time 0, which is the 2 feet. That first period, I totally messed up, and I used the 26 for the initial speed. But we kind of need that to be in feet. So how many feet is that? Just times 3. So, and my mistake, really my big mistake, is I wrote these numbers without units, and so I managed to screw everything up. All right. Now, we want to find how far it travels horizontally, which the horizontal equation gives us to you, except for we don't know how long it took, how long it was in the air. So what we're going to do is use the vertical equation to find how long it was in the air. And how do we know when it stops flying? When height is 0, right? So let's set it up like this. By the way, I don't like the way I meant to fix this. Really, you'll have numbers here. Notice t will be your variable, okay? So I'm going to write this with the speed and sine of theta. I'm just going to put t after. I just like it better that way. So I'm just plugging these numbers in, putting the t there. Now, the acceleration due to gravity is, if metric, would be 9.8 meters per second squared, but we're not in metric, so it's 32 feet per second squared. So in these problems, you always use 32 feet per second squared. Which half of that is 16, so I'm just going to put minus 16 feet squared plus 2 feet. Now, here's the deal. And in fact, watch this. You don't do anything on your calculator yet. We were in parametric mode. We wanted to go to the calc menu. You do second trace, second calc. These are the things you can calculate when you're in parametric mode. Not helpful for what we're trying to do. So what I need you to do is go back to function mode. And type in your equation into y1. Now, we want to get this, parabola to appear on our screen. What's a good estimate for the tallest, like how high a football do we go when you punt it? In feet. How high does a typical punt go? Give me a guess. I mean, more than 10 feet. I want a number to put in for y max. 1,000 is a bit unreasonable. 70 feet. So let's try y max. Now I need to change all of these things. So, by the way, one big thing you need to realize is we're in function mode, but in reality, in other words, we're graphing the height over time, right? So when I did this first period, I said, oh, well, the x-axis, we'll make it like 60. Because if his average is 46, and he's gone more than 46 sometimes, right? So I made the x-max 60. And what we got was a graph like this, because 60 would be 60 seconds. And punts don't stay in the air for a whole minute. They just don't. And so a better estimate for how long it's in the air is a few seconds, like 5 seconds, 6 seconds. So, and then the y values, we said, someone said 75, let's try that. Okay? And hit graph. that it went above. And frankly, for what we're doing, we don't need the max, but you will for some of these applications, so just play with it. I'm going to bump this up. It's actually like 111, 112, I think is what we're going to get. I'm thinking of a different problem. Okay, yeah. Anyway, on the worksheet, you're going to have to find the maximum sometimes, and so maybe, and in fact, let me show you that. The problem didn't ask for that, but I'll show you that as well. Right now, let's just answer the question of the problem. It wants to know where it hits the ground. That's what we're trying to find right now, yes? So for that, you have two options. You could do this. Look, you can do calculate the 0, but you can also do second calc 5, where you find the intersection point, which is easier. Here's the catch, though. If you want to find the intersection, you have to have two equations. So in other words, go into y2 and put y equals 0. So it actually has the x-axis drawn there. And once you had y equals 0 typed in, now you can do second calc 5. And you can press enter, except for one thing. Listen, before you press enter 3 times, there's 2 x-intercepts. We want the one on the right. The one on the left, by the way, would be negative, because it started off the ground, right? But we want this one. So I'm just saying, make sure your cursor is closer to the right-hand one before you press enter. And when it says intersection, you know you have your answer. That's 4.66 what? Seconds. I didn't want to do that. Okay, so write that down. So t worked out to 4.66 seconds. Except for that's not the answer to our question. We want to find out how far it traveled. So how do I do that? I use this horizontal equation. So we'll do 4.66 seconds. Before we do this, watch this. The nice little thing is, when you calculate, when you calculate an intersection point, it stores it. On your calculator, press X, type X, and press enter. And you'll see it stored that value in there. And if you want the Y value, that's stored in Y. So here, you don't have to type it in. You can just, we're doing that times the 78 times cosine of the angle. But here you can just do X times the 78 times cosine of the angle. And so you get 112.4 feet. So we prefer yards for this. 3 yards per foot works out to 37.5 yards. That's how far the punt traveled, how far the football traveled. Yeah. So it wasn't a good day for him, or it wasn't a good punt at least. Now before we put this away, go back to here, and I want to show you how to find the max. So I'm sure you have the equation ready to go. Hit second calc, choose number 4, do this in your calculator. Second calc, max, which is 4. And this is different. You don't just press enter, enter. You have to define where you want to look in the graph. Because it could have multiple maximums, okay? And so when it says left bound, put your cursor to the left of the center, or the maximum, and you just have to kind of eyeball it. By the way, isn't this 0 over here? I'm saying you can cursor over, which would be kind of a pain. It's not horrible, but you can cursor over, or you can just type in something that's left of the center. 0 is on the screen, it's left of the center, so you can just type it in. For the right bound, this was what, 5 seconds here, 6 seconds here, right? So I'm saying you can cursor back to the right of the center, or just type in something that's bigger than the center. And when you're done, what you'll see is there's an area here, and another area you can't quite see, but it's going to look in that part of the graph and find the maximum in that part of the graph. And for when it says guess, I would just press enter, don't worry about it, just let it calculate. And so it turns out maximum height was around 88 feet, and it happened after 2.3 seconds. By the way, the other way we could have found that Well, no, you gotta be careful about this. I was gonna say you could take half of this. The problem is it didn't start out on the ground. So it's not halfway from 0. I mean that is, it's close, but it's not exactly halfway. So really you need to do it that way. All right. Yeah, here, I'll show you again, okay?